everyone, my name is Mariah Smith, and for this graduate article review, I will be discussing the environmental impact of wind turbines. All right, so first just go over an overview of this presentation. I will first start with the learning objective, and then I'll go into the introduction of wind energy production, a life cycle inventory of wind turbines, the methods for this specific study, and then an assessment of the current environmental impact, and an assessment of the projected environmental impact, and then I'll end with some conclusions. All right, so the learning objective of this presentation is students will be able to identify what wind turbine materials are projected to have the highest environmental impact. So as we all know, within the next 20 to 30 years, by 2050, we are expecting a big increase in renewable energy production. And the use of non-renewable resources such as coal, oil, gas, and uranium is actually expected to decrease by 43.2% in 2050 worldwide. And today, comparing that to just wind energy production, wind energy represents about 5% of all electricity generated globally, and only 9% of all electricity generated in the United States. And looking at the specific projections for renewable energy by 2050, the total amount of renewable energy power from sources such as wind, solar, geothermal, and hydropower should actually increase by 551.7% by 2050. And the specific wind energy contributions are expected to grow by 30% in 2050. And just to provide a little example closer to home, there is actually a 240 turbine wind farm located in eastern New Mexico, which is owned and operated by Xcel Energy. This is the largest wind farm in New Mexico, and the energy production started at the beginning of this year, and it can produce enough electricity for nearly 194,000 homes. And there's also a 40% more generating capacity than any of the next largest facilities within the state. This energy source actually powers both New Mexico and Texas, since it is right on the border, as you can see in that figure on the right. But this will actually help Xcel be 80% carbon free by 2030. All right, so getting into the actual wind turbine components before we start getting into the whole analysis of this study. The major components of a wind turbine consist of the tower, rotor, and nacelle, and then also the foundation, which isn't shown in this picture. So a tower's height is crucial for turbines because wind speed increases with height, and this is why most turbines are created to reach heights between 50 and 150 meters tall, where the wind is high, but the load stays low due to turbulence. And then the rotor consists of the blades of the turbine, which act as barriers against the wind. And when the wind hits the blades, it forces them to turn and activate the generator, transferring the wind force into electricity. And then the last part, the nacelle, is part of the turbine that houses the components that transforms the wind's kinetic energy into mechanical energy to turn a generator that produces electricity. And then of course the foundation connects the tower to the ground and bears the static and dynamic loads created by the turbine. All right, so the overall goal of this work is to evaluate the material requirement associated with the large-scale deployment of wind energy in the United States and the rest of the world. And so if you can see in this life cycle inventory here, we're looking at the specific materials needed for the entire assembly. So we're looking at the tower, the nacelle, the rotor, and the foundation of both offshore and onshore wind turbines. And so the specific materials needed are steel and iron, copper, aluminum, fiberglass, polymer, epoxy, and rare earth metals. And also additionally concrete, gravel, and steel and iron for the foundation. But the rare earth metals comprises of 17 different elements with similar properties, but the rare earth metals of the highest importance are neodymium and dysprosium. dysprosium. And the three environmental impacts that were assessed with respect to these material requirements was the number of raw materials needed, the carbon dioxide emissions, and the cumulative energy demand. All right, so getting into the actual methods of this study, in order to assess the environmental impacts of wind energy or wind turbines all the way out to 2050, this study relied heavily on wind energy forecasts and projected material productions. And first they did that through looking through historical data from journal articles, life cycle assessment reports, and the EcoInvent database. But they also used three different wind energy forecasts, which were the Energy Transition Outlook from the government, private companies, and the Department of Energy Wind Vision Study. And they used this current information to project material requirements for wind turbines all the way out to 2050. And the future mass intensity of these wind turbines, given the energy forecasts, was determined, and the future material requirement to supplement that amount of wind turbines was estimated. And so as you can see here in the figure on the left, this is the amount of different materials per megawatt needed for wind turbine projection throughout the years. And so as you can see, it's been consistent that the highest amount of material needed is gravel and concrete, and the rare earth metals, which are considered the critical materials in this study, have a much lower material requirement per megawatt. And that ties into our functional unit, which was 1 megawatt wind turbine. And the focus of the study here is that concrete and steel are the most important materials by mass. And although the rare earth metals receive a lot of attention due to their high economic importance and supply risk, they represent only about 0.03% by weight of all materials used for the onshore and offshore turbines. And so we're really wanting to look into kind of the comparison between concrete and steel and the rare earth metals, since the concrete and steel are going to be considered the non-critical materials, and our rare earth materials are going to be considered our critical materials. All right, so this is the raw element requirement based on historical data. And as you can see, this is the quantity of raw elements mined to obtain 1 ton of each material used in wind turbines. The rare earth material production is more intensive than the non-critical production, and in total, the REEs require 594% more raw elements mining than the non-critical materials by comparing 1 ton of each material used in wind turbines. And then the production of critical materials is less intensive than the non-critical materials, considering the quantity per megawatt. So keeping this information in mind, this is the current environmental impact of wind turbines today over time. And this figure compares the global warming potential associated with critical and non-critical materials per megawatt of onshore and offshore wind turbines. And so as you can see in the figure, the carbon footprint of the non-critical materials is larger than the impact of the critical materials. And of the non-critical materials, steel and iron had the highest global warming potential. But this was actually interesting because concrete has the highest mass intensity. So even though concrete has the highest mass, it didn't have the highest contribution to the global warming potential. And additionally, on average, the impact of the non-critical materials is higher for offshore turbines than the onshore turbines, as you can see in the difference between the figure A and figure B. And then the rare earth element impact is about 42 times lower for the offshore turbines and 24 times lower than the onshore turbines. This is mainly due to the small amount of rare earth element material needed in comparison to the non-critical materials. All right, and so this, we're getting now into the future material demand based on those projections from the forecasts. And so as you can see in these figures here, there's 4 different data sets, which is the the three different forecasts used, and then also the expected production of each material. And so the first graph is the cement production compared to the future material demand. And then the figure B is the steel production compared to the future material demand. And then on the right-hand side is the low and high scenario rare earth element production versus demand. And the low and high scenarios for the rare earth elements are dependent on if future wind turbines actually utilize permanent magnets in their generators, which requires more rare earth elements. But as you can see in all figures, the concrete, steel, and iron and rare earth element demand will change over time based on all three different forecasts. But the demand compared to the total or the total production of each material is still quite dramatic. And so you can insinuate that the future material demand isn't going to make as much of an impact compared to the projected production of each material. But it is important to note that a shortage of materials could potentially happen depending on the future wind capacity installed and the global demand for the same materials in other applications other than wind energy. And so this ties into the projected environmental impact all the way to the year 2050. And so as you can see between the four graphs, which use the different forecasts, there's a big difference in the estimated global warming potential. And so looking at just specifically figure D, which is the global warming impact and seems to be the most conservative, the total carbon footprint associated with the global production of all materials to construct wind turbines in 2050 is about 108,000 tons of carbon dioxide equivalent, which is equivalent to the amount of greenhouse gases emitted from about 91 gigawatt hours of electricity produced by a coal power plant today. And this projected global warming potential from the production of materials to construct wind turbines in the USA and the rest of the world in 2050 is about 9.3 times lower than the carbon dioxide emitted currently from coal power plants in the United States. So even though this, especially figure D, looks a little dramatic and a little bit of figure A, it's still very minimal compared to our current coal production today, which is quite interesting, given the amount of materials that are needed for wind turbines. And so just a little bit of conclusions. This study aimed to estimate the material demand for wind turbines in the United States and the rest of the world until 2050 and the associated carbon footprint. A major limitation is the forecasting of the wind turbine utilization. As you could see in the last slide, there was vast differences between the three forecasts used for these projections. And so they could be either too conservative or not conservative enough. And then also this work did not consider the increasing demand for other technologies, such as solar energy, electric vehicles, and energy storage that could affect some of these projections. And then also this study only considered primary materials and not recycled materials, which is actually a big thing today, because the lifespan of a wind turbine is only 20 years. And recycled materials is something a lot of people are looking into because we haven't figured out exactly really how to recycle these wind energy turbines yet. And so given after 20 years, we're just wasting all of these materials, and the use of recycled materials might actually benefit that impact. But the findings overall prove that wind turbine energy will have less of an impact in 2050 than current coal energy production. But again, this projection was only for around 35% energy production in the future, and wind turbines and other environmental impacts could play a factor, especially disposal, since we don't know about recycling them yet. And so the overall message should be that reducing the material intensity and associated environmental impact of wind turbines is critical, considering the increasing number of wind farms expected to be built in the next 20 to 30 years. And so even though the impact was successful, we shouldn't stop there. We should keep trying to find ways to reduce the environmental impact no matter what. All right, and these are my sources. I hope you enjoyed this presentation. Thank you very much.